Hello everyone. Today I'll be talking about plain ciphertext attack. So uh, I was provided with an data set of uh, plain text and its equivalent ciphertext, as well as the ASCII encoding of uh, plain text from hexadecimal to ASCII and ASCII to hexadecimal. So basically, it was a JSON file with three attributes. They were the ASCII object, and then ASCII string object, and then its equivalent hex string, and then the uh, encryption of the hex string. So, firstly, I take the frequency of uh, messages of same length in both uh, plain text and ciphertext, and it was not much revealing except the fact that some of the blocks remain unseen in size. And then I checked for the uh, length uh, of cipher and length of plain text and mapped them together and stored it in a line chart. We showed that there wasn't any dependency between them, but one interesting thing was uh, we take the length of the plain text and map it to its nearest multiple of 32, and then we map it with the length of the ciphertext. Then we can see that there is a linear relationship between them, which shows that the ciphertext, every ciphertext in the given data set are in multiple of 32 in their length. And this doesn't reveal much. So, and next, what we did was we took the first row of our dataset after converting it into a pandas data frame from JSON, and then we took the first row, uh, the first tuple of hexadecimal representation and its encryption, and then we counted the occurrences of each hexadecimal characters, and then uh, stored both of the unique characters, and its frequency in a set. And only looking at the first tuple or only one tuple, it seems that there is some sort of relationship between the occurrence of the characters in encrypted text and the cipher in the original text. But if we look at the bigger picture, mm, and when you take the entire data set, there is a kind of entropy in the distribution of characters in ciphertext. We can see uh, the orange line here represents the hexadecimal characters frequency in ciphertext, and the blue line dot represents the uh, frequency distribution of message. So, mm, uh, what we can conclude from here is that the given encryption which maps our message to the ciphertext is not a substitution-based cipher, and it is not a linear cipher because there is entropy uh, present in the ciphertext after encryption. And another thing is that it is a block cipher because we can divide the ciphertext into a fixed blocks of 32 for every data set. So from here, I guess that it is AES based encryption. Uh, yes. uh, and then went on to implement the AES encryption. Mm, because one thing that hinted towards uh, AES encryption being the method for encryption is that if I take a common substring uh, from the unknown or the given message, and then try to map it with the length of uh, common substring from the encrypted message, then that is equal, which means that uh, and their length is also 32, which means that uh, for the uh, for a common substring of given message to map to the exact common substring of the message, then its length will be 32, which means that this is indeed an block cipher. And since it is non-linear, it is almost always safe to assume that it is some kind of AES-based encryption. So here uh, we are halfway down the road, and we found the nature of the function, that is the AES-based encryption. And uh, then yeah, this is just mathematical representation of what our original problem was, and I'm going to discuss much about it. And then this is the high-level overview of AES encryption, in which we take a substitution box table, and then shift and then map it with the given uh, byte, hexadecimal byte, which is the two-digit hexadecimal representation from block of 32, and then shift the rows in order, uh, such as the first row is unchanged, and then second row is shifted by one byte, and third row is shifted by say 2 bytes, and so on. And this and then the resultant matrix is multiplied with a mixed column matrix, and then round key is added by XOR operation to the resultant matrix, which is repeated for 9 times, since it is a 128 bit AES encryption. And then we perform another last round, excluding the mixed columns, and then we'll get our encrypted message. So this is what happens inside each software inside the AES encryption. So this is how substitution works, as I explained before. And then AES mixed column is represented in its mathematical interpretation as uh, shown here. And then finally we will use the add round key. Now, after this, I implemented an AES encryption and decryption algorithm, and I created a brute force attack to guess the key. But since we all know AES encryption is uh, because it has so many permutations, it's computationally able to find the key, and you can see the result. It took almost 588 minutes before terminating and not being successful in finding the key. But provided int for key or substring of the key, it will be possible to uh, find the key of the algorithm. Now we'll see the demo of implementation. Look at the yes implementation. First, we imported the data set and turned into a pandas data frame, and then we try to uh, determine the encryption algorithm for the first uh, first byte block, first 32 sorry 16 byte block, and then try to generalize the algorithm for every data set. So then we created a uh, two functions to convert from hexadecimal to a decimal and decimal to hexadecimal for easier handling of the mathematical operations. And then this is the predefined mix column for standard AES encryption algorithm. And this is the substitution box which will require later. The substitution box is of shape 16 by 16 with 256 bits, 256 characters mapping to another 256 characters, and which is non-linear, and in distribution it is chaotic. Then we define functions for each sub operations of the AES encryption, which is for substituting the byte and then shifting rows, and then mixing the columns, and finally bitwise or for adding the round key. So this is a single iteration for AES round operation except the last round, and this is implementation of the last round. This is combined AES encryption algorithm. And then in similar way implemented the inverse AES operation for decryption. Now let's take a string and try to find its encryption. In this way it maps from 16 byte hexadecimal representation to encrypted another 16 byte hexadecimal representation, but because it is a 128 bit AES encryption, the key size is also 128 bit, and to get the exact key is almost computationally impossible, because we need to get the permutation up to the power 128 bits and choose one from it, and getting it correct is near to impossible. And then we encrypted the messages, we decrypted the ciphertext back into the encrypted the plaintext, and I think we are not getting it matched with the original input. Maybe there is some fault in implementation. I'll try to fix it. And then as I mentioned before, I tried to brute force the attack, but it did not work because of the sheer number of permutation that have to be taken into consideration while trying to plan a brute force attack on AES encryption. And with a hint to key a key of the AES encryption or the nature of the key, it will narrow down the source and you will be able to crack the actual algorithm with parameters. But here we have cracked the encryption and decryption method, but without the parameter, which is the key for encryption and decryption. So since it is a symmetric key encryption, getting a hint on key will be very helpful for planning attacks, given that both message and ciphertext are provided.